Hello 171 class, this is part 2 of your notes for section 3.5, and what we're going to start talking about here is something called half-life. Half-life is how long it takes something to get from what it started with down to half of what it started with. So it starts at 1, it gets down to half in this amount of time. Alright, this time right here is the half-life. And it doesn't matter what the initial amount was. For instance, like I have 1.5 here, but if it had been 10, now it's getting down to 5. Okay, if it had been 100, it's getting down to 50. Alright, but what we use when we're talking about exponential decay is A0 is the original amount, and we're getting down to half of A0. Alright, so what this is telling me in this problem, right here, if I replace the A with half of the original amount, I get 1/2 A0 equals A0 e to the kt. So I just put this in right here. That's how long it's taken to get to half the original amount. Okay, now we're told it takes 12 hours. So we're going to take that t away and replace it with 12. K times t, so k times 12. Now once again, like I did before, I'm going to write that as 12k instead of k times 12. Okay, so we plugged in half to get this 12 hours. It gets down to half of what it originally was. And now we literally go through it and solve for k like we did before. It's just this number that we're dividing by is an unknown value. It's the original amount. But we can divide it away because it's the same thing on the other side. And now the A0 is going to cancel on both sides. And we end up with half A0 equals e to the 12k. Alright, and just like before, like we did in the first part of the videos in this section, we're solving for this exponential, the variable in this exponential equation, so we're going to bring in natural logs. And as it always does, natural log and e wipe each other out, and this power falls down. So we end up with the natural log of 1/2 equals 12k. Remember, we're solving for k, so we're going to divide both sides by 12. Alright, so we end up with k equals the natural log of 1/2 divided by 12, okay, which is approximately negative 0.0578. Alright, remember it's decreasing, so k should have been negative, so it's fine that we get a negative there. So negative 0.0578. Alright, but remember what we're doing with this. We're taking this k and we're plugging it back into the original. So we end up with A equals A0 e to the, this is k, so negative 0.0578 t. Alright, so that's the first part of this. But then it says, how long will it take for the aspirin to decay to 70% of the original doses? Well, that's A, so that's 70% of A is 0.70 times A0, 70% of the original, right, that's A0, equals A0 e to the negative 0.0578t. And now we're going to do the exact same thing that we just did, but now we're solving for the t instead of the k. Alright, so just like before, we're dividing both sides by A0, and that's going to get rid of A0. And then we have the 0.7 equals e to the negative 578t. Bring in the natural logs to get rid of the e. Alright, you got to do it on both sides. Alright, the natural log and e wipe each other out. Natural log of 0.7 equals just now negative 0.0578t. Alright, then I'm going to come up here, one last step. We're going to divide both sides by this number in front of t, so that cancels and we're left with t equals the natural log of 0.7 or 0.70 divided by negative 0.0578. Alright, and then plug that in your calculator, obviously, to get an approximation. Alright, natural log of 0.7 divided by negative 0.0578. I hit enter. So there's about how long it takes, the half-life. The T is approximately 6.17 hours to get down to 70%. Alright, now I left this on the calculator on purpose. The natural log of 0.5 divided by 12. Alright, because that negative 0.0578 that we divided by here came from that. So I'm going to show you a little shortcut for a problem like this based on this calculator screenshot that we have right here. I'm going to put it into our sheet and show you how I can use this to come up with a shortcut. Alright, so what I'm going to do here, I'm going to take this, the 0.0578, and I'm going to replace it with what we used to get it. So we took the natural log of 0.7 and we divided by this negative 0.0578, but that was the natural log of 1/2 divided by 12. Okay, all of that's the denominator. Now this is a fraction, so we're dividing by a fraction. So instead of dividing by this, I'm going to write it as the natural log of 0.7 times, remember how you divide by a fraction, you flip this thing and you multiply. So the natural log of 1/2 goes down to the bottom, 12 goes up to the top. Now just because this is, I can write this as that over 1. When I multiply these, I end up with a natural log of 0.7 times the 12 over top of the natural log of 1/2. Alright, and the last thing I'm going to do here is I'm just going to pull the 12 out in front. Okay, the reason I'm doing that is because the 12 is just a whole number, then the natural logs are here together, and what I want you to see is, like if I have, for instance, 5 times 3 divided by 4. Alright, if I have that, I get 3.75, but if I put this number out in front, that would be like the 3. If I put the 3 out in front 3 times, and then had the 5 over the 4, in parentheses, like they're together, I still get the same thing. So if I put this 12 out in front and still have these two together, I still have the same thing. And I'm writing it just for a reason, just to give you guys a little shortcut formula. And this natural log of 1/2, you can write it as 0.5 or 1/2. But what we end up with is a little formula to get this same number. It's actually a little bit more accurate than that number, but 12 times the natural log of 0.7 divided by the natural log of 1/2, which is again 0.5, still gives us roughly that same number. Okay, just because of rounding, we see a little bit of a difference. This one's not rounded as the other one was because it had the 0.0578 instead of this entire expansion or this entire expression. But what is this? Go back and look at the original problem. What are we dealing with here? 12 is the half-life. So what we end up with is you can take your half-life that you're given and then multiply that half-life times the natural log of the desired percent that you want it to get to, or you're being asked about, and then divide that by the natural log of 1/2. It's like a ratio. The half-life is what we're given, but we don't want the half-life anymore. We don't want it to be down to 1/2. We want it to be down to, in this case, 70%. Right? Or if the problem would have said, how long does it take something with a half-life of 12 hours to get to 15%, then I would do 12 times the natural log of 15% as a decimal, 0.15, and divide that by the natural log of 1/2. And there's how long it takes to get to 15%. If I wanted 30%, then I would write 30%. It doesn't take as long. If I wanted it to be all the way down to 5% remaining, it's going to take longer, and 51.8. So this is a nice shortcut if you're given the half-life and you're being asked how long does it take to get down to some other particular percentage remaining. Alright, so here's three really nice formulas that that are used a lot in this section. Shortcut formulas that you can use a lot for this section. So it's worth your while to pause this video, write these down, and put them in a place that you can have, or even just have it out for you, especially for a quiz, because these are the three things that we compute, and these are the information that we're given a lot of times. So two ways to solve for t. One, the natural log of the percent that remains divided by k if you're given k. If you need to solve for k and you're given a half-life, it's always, every single time, the natural log of a half divided by the half-life. And then the one we just did, what if I'm given the half-life and I need to find out how long it takes for some other percentage to remain, then this formula applies. So these are three very useful formulas for 3.5. Alright, so here's an example where we get to use one of those formulas. So this one says skeletons were found at a construction site in 1989 and they contain 88% of the expected amount of carbon-14 found in a living person. So this is the decay rate of carbon-14. Alright, there's the value for K. So how old is that thing in 1989? Well, the time that's been decaying is equal to the natural log of the percent that remains, the 88, divided by K, which is this value in front of the T here. Alright, so we plug in 0.88 because it's a decimal form of the percent that remains, and then the negative 0.000121 for K, and then just plug that into your calculator. Alright, so I plug that in, enter, 1056.47, so roughly 1056 and a half years. Okay, usually they'll ask you to round to the nearest whole, but just make sure to look at the right decimal place and round accordingly. But the point is, these formulas, they cut out a lot of work. You would have to do, this type of stuff every single time that you solve these formulas, or solve these problems. You'd have to go through and do this type of stuff each time, but it's always the same thing. You plug in, you divide, you take a natural log, that gets rid of the E, you divide by the thing that's with the K or with the T in this case, and you always get this same type of setup for the work. You always do the exact same thing every single time. So why not just go straight to the, cut the chase and go straight to the end with a formula like this and cut out those 6 steps that are always the same, those 6 repetitive steps. Just use the formula. Okay, so you just have to know what formula to use when. So again, this formula applies when you're given a percent that remains and you know K either from the formula they tell you in the problem statement.